Hello, I will be demonstrating how to simulate a horizontal flat plate floor in Fluent. First, drag the standalone system into the workbench, click on Geometry, and set the analysis type to 2D. Then we open up a new design model geometry. Once this is open, orient yourself so that the XY plane is at the front. Then we draw a rectangle. Then we add the dimensions. Because we're working in centimeters, set the units to centimeters. We want a flat plate that is 30 centimeters long and 0.1 centimeters thick. Now we zoom in, and we also need the place where the fluid flows. So we're gonna add another rectangle, draw it over here, and that will be what generates the flow. Now the sketch is done. We go to Concept, Surface from Sketches. We click the sketch, use it, generate it. The geometry part is done. This part is great, hollowed out, because that's where the flat plate is. We're done with this part now. Now we go to Mesh. Now that it shows up, we want to add an automatic mesh to this. The automatic mesh is done. Now we insert a refinement of 3. We select the face, generate it, and now we want to add a new sizing. Select the top plate and the bottom plate, apply it, change it to number of divisions, use 200. And then generate it. Now the mesh is generated, so it's much finer here, but we also want to add another sizing at the front part and the back part. And we want to set the number of divisions to 50. Now the meshing is done, and one more thing we want to do before we move on is to name the part. So select the top plate, name it top plate. It's a keyboard shortcut, you just press N. So we just name all of these parts. Front plate. Back plate. Remember to name the inlet and the outlet. Everything is named correctly and we're done with the meshing. Update the mesh. Just so you know, the second sizing we used was not necessary for the other 2 cases. It was only necessary for this one. The first thing we're going to do here is change the model to K epsilon with enhanced wall treatment and pressure gradient of X. Next, we're going to alter the materials. We're going to change the density to 1.2 and the viscosity to 1.8. Now, we go to boundary conditions at the inlet. set the inlet velocity to 50 meters per second because that's going to be the free stream velocity. Nothing else needs to be changed here except for reference values. And the area is going to be 0.3. The length is going to be 0.3. Change those so that you can get accurate coefficient of drag calculations. If not, you can just use the force method to get the coefficients. Another thing we want to do is set the residuals smaller to get more accurate results. But you don't need to do this, this is optional. The other thing we want to do now is go to report definitions and use this to compute the coefficient of drag. So we're gonna use the plate parts and it's gonna output the drag coefficients. We're gonna name this drag, close, and now we're basically done and we solve for this. You're gonna want to increase the number of iterations to a lot. This doesn't matter because eventually it's gonna converge and it'll stop before that number is reached. So you're gonna see the coefficient of drag being calculated and also the residuals. Okay, it's done. So now you want to go get the coefficient of drag, compute. This is our computed drag coefficient. The force method, if you go to reports, forces, select the plate, print. You get the coefficient. Since here, you also get the forces due to pressure and viscous forces. So that simulation is completely done. Now we're going to go into the results to post-process our data. Make it face the correct directions and let's input our contours. Velocity contour, symmetry 1, 200 contours, set the thing to velocity. So that's the velocity. We're going to change the legend so that it's not scientific and you can actually read it properly. We also want to add in the velocity vectors. These are the velocity vectors. You want to reduce this so it's more readable, but for this case it's not really going to become readable at all. We have to do a lot of reduction. But the only information this is telling you is that the flow is moving in this direction, speeding up at the tip, but you could have seen the same thing here if you just zoomed in. It was a little obvious. But the other thing we need to do is the pressure contour, so we're going to add that. And this is what it should look like. The pressure increases at the stagnation point at the front, and there's a very small wake region here. And that is part A done. Aaron will be handling part B, where he shows you how to get the boundary layer thickness and shear wall stress as a function of Reynolds number or something.
Hi everyone, this is Aaron, and I'm going to be showing you guys how to do part B of Fluent Project 2 for Dr. Osbay's Fluid Mechanics Honors class. All right, so I'm going to show you guys my screen here. Okay, 1 second. All right, so first what I'm going to do, that's a little bit better right there. Okay, so first what I'm going to show you guys how to do is how to get the velocity profiles of the boundary layer at 10 centimeters and 20 centimeters on the plate. First, what you want to do is you want to create two lines. Line one, you can zoom here, turn the velocity contours. Okay, line one is the line on the left. And to do that, you just want to put 2 points, one at the top of the plate at a distance of 10 centimeters away from the right side, and then another point further up from the top of the plate. I chose 0.02 meters. I'm pretty sure that's 20. No, is that? I don't know what that is in meters. I cannot do math right now. But anyways, yeah, 0.02 meters above the flat plate. I chose for that, and that's to allow enough room for the flow to fully develop. So, or to not fully develop, to reach the free stream velocity again, because we want to capture the entire boundary layer. So after that line, you're going to want to create another line at, instead of 10 centimeters, create it at 20 centimeters right there. It's the one on the right, and do it at the same height. So then after that, you're going to want to go to your report section, and you're going to want to create a new chart, and that's a velocity profile. Oh, I just thought I mentioned, make sure your lines, you take a bunch of samples, about like 1,000, excuse me, 1,000 on each, because if you don't, you won't get a smooth line. It will look very jagged, and it won't look that good. It won't give you a good representation of behavior. So first, the velocity profile, all you have to do is plot velocity on the x-axis and y on the y-axis. And you can see the way I did it, you can either look at the graph or you can export this into Excel. The way I found the boundary layer thickness, all you have to do is just look and see the y position when about 15 meters per second is reached again, or as close to 15 meters per second as you can get. In this case, I got a value of roughly 0.06. Yeah, about 0.06, somewhere around there is what I was looking at. And then for velocity profile 2, you do the same thing, but you plot the velocity. You plot the first velocity profile, you're plotting on line 1. Second velocity profile, you're plotting on line 2. So as you can see, this profile at velocity 1 is actually more turbulent than the profile at velocity 2, which is some pretty interesting behavior considering that's a flat plate. And this is due to the fact that the flat plate actually has a thickness. It's not ideal. But anyways, now we can talk about how we get our plot of Reynolds number versus wall shear stress and versus skin friction coefficient. So there's one way like you can do this. You can get your plot for the Reynolds number. If you go here, you can see that I got a plot for wall shear versus Reynolds number. This is in the Fluent solution, the post-processing. You can also do, I'm pretty sure, another way. Okay, I'll show you guys how to do this way. This, all you have to do is create an expression, but in my opinion, this way I found to be kind of I found there to be an easier way. I'm going to show you guys that way instead. So all you have to do is you have to go into your solution. And if you go to plots, click on plots, then XY. Okay. So what you should do is you should look at wall fluxes and you should get skin friction coefficient. Or we'll start with shear stress. Start with shear stress and then your x-axis function, do your direction vector. And then once you get this, you're going to get an Excel spreadsheet that you're obviously going to have to write to a new file. So do top plate and then click, make sure you write to file. Once you write it to file, you're going to get an Excel spreadsheet that looks something like, I'll show you guys instead. Let's just make a brand new file. It's probably easier to show you. We'll write that to, we'll call this wall shear example. Put this in Fluent Project too. Yes, okay. So here's what you're getting. This is wall shear. This right here is X, and this is wall shear. As you can see, we have a bunch of different samples. X is going down, wall shear is rising. So what you want to do to plot this, since Reynolds number is only dependent on X in this case, because density is constant, your free stream velocity is constant, and your viscosity is also constant. All you need to do is create another row or another column in Excel with your Reynolds number and plug in the formula just like usual, and then plot just like you would with Excel, anything else. Plot skin friction coefficient on the Y and Reynolds number on the X. And you should get a profile that looks like this. It will be very jagged. You can add a trend line if you want. Compare that with a theoretical. It's same behavior, but obviously there's a lot of erratic behavior, and that's due to obviously because you're looking at a non-ideal case. So for the skin friction coefficient, you're going to do the exact same thing, but you're just going to do, instead of wall shear stress, just click skin friction coefficient right here. And I'm not going to show you guys to write to another file. It's literally the same exact thing that we just did, but with skin friction instead of wall shear. And for that, that is about it. I'm pretty sure that's everything that I need to show on this video. And yeah, thank you guys.